If you read the course description of 2.2x, you'll have seen that I was promising that you would hate gambling after you're done with it. You certainly hate roulette by now. All those minus signs, never, never, never. Are you going to play roulette? I hope. I also said that we'd answer questions like, how can a poll be accurate if it's based on only a small percent of the voters? And politicians face this all the time. So there's some poll that's taken, and candidate A does not like what the poll says about his or her chances. So candidate A, the first thing they will say is, well, you can't trust polls. How can you trust polls that are based on such a small fraction of the population? Polls don't mean anything. Well, let's see. And one of the beauties of making Stat 2.2x available freely online is maybe one day a politician will actually take it. All right, so we'll take an example. I have a population of 1 million voters, and I've taken a simple random sample of 1,000 of them. And we are trying to estimate the percent of voters who will vote for candidate A. So this sample, as a fraction of 1 million, is indeed quite small. So this is one with 3 zeros, this is one with 6 zeros. I've knocked 3 zeros off, which means I've taken 1,000th, that is 1/10 of 1% of the population, as my sample. A tiny, tiny percent. And so no question, I have sampled a very small fraction of the population. So if I'm trying to figure out how good my estimate is going to be, I need to figure out the standard error for the sample percent. So what are the ingredients in that? Well, one of the ingredients is the correction factor, which if you have a sample of size 1,000 and a population of size 1 million, you can work it out. That correction factor is awfully close to 1. And no matter what, it's certainly less than 1. Okay, so what else goes into it? Well, standard error for a sample percent is the square root of p times 1 minus p divided by sample size. And so what's p? We'll have no idea. But what's the worst case scenario? What's the biggest that error can be? Do you remember? A couple of segments ago. The fair coin is the most variable, and so the biggest your standard error for the sample proportion can be is if you put p and 1 minus p both as 0.5. We went through this. And so there's a calculation now. Square root of 0.5 times 0.5 divided by your sample size of 1,000, and that's 0.016. That's 1.6%. Actually, I think it's 1.58, but 1.6% roughly. And so what have you seen? What you've seen is that with a sample size of 1,000, your sample percent is expected to be within a couple of percent of the population percent. So within 1.6%, within 3.2%, within 4.8%, beyond that, surely not. So I think it's reasonable to say that there's a very high chance that the sample percent will be within about 3 or 4% of the population percent. And so even though you are sampling a minuscule fraction of the population, the error in your estimate of the percent is not huge. You're going to get your answer right to within 3 or 4% with overwhelming probability. And so the politician, unfortunately, if his or her poll is not giving the results they like, they can count on the very small chance that we're off by a lot, but really the very high chance is you can be pretty close. And what I'd like to do now is to take this discussion of accuracy in stages and just look at which factors are affecting accuracy and which factors aren't. So we are going to be pretending in our minds that we're estimating a population average or a population percent, or we're looking at a random sample average or correspondingly a random sample percent. And we're looking at the accuracy. In other words, we are going to look at the standard error, and for an estimate to be more accurate, the standard error has to be small. So as the sample size gets larger, what happens to the standard error for the average? Well, the standard error for the sample average is population SD, which is fixed, divided by the square root of the sample size. So that's going to get smaller as the sample size increases. There's the other component of the standard error, that is the correction factor, and that's square root of population size minus sample size divided by a constant. That also will get smaller as you increase the sample size. So as you increase the sample size, both of the factors that contribute to the standard error of the sample average get smaller. What if you were doing a sample percent? The only thing that would change here is that you'd have a particular form for the SD of the population. It would be sigma, but sigma would be the square root of p times 1 minus p. So everything we're saying about what happens when the sample size gets larger is the same for sample averages as it is for sample percents. So you're increasing the sample size, then the SE of the sample percent and the SE of the sample average both decrease. In other words, as you increase the sample size, the sample average and the sample percent become more accurate. That's because of how the sample size is placed in the formula for the standard error. And that's a very natural sense. The bigger your sample, the sharper you're going to be at estimating averages and percents. Okay, so how much sharper? I'm going to work in the situation where, as typically in statistics, we have a very large population and relative to that a fairly small sample, and so that the finite population correction, our correction factor, is approximately 1. I'm not going to be bothering with that. And I am going to be fussy. I'm going to say I don't like the accuracy that I've got now. I want 3 times the accuracy. As you know, in this class, you start fussing, well, then you're hard to satisfy. And I am being very fussy. I want 3 times the accuracy. Let me first define what that means. I'm going to define 3 times the accuracy by saying I want the standard error to go down by a factor of 3. Right? This is a measure of error, and I want less of that. And I want less of that by a factor of 3. So what do I have to do? Well, I've got to increase the sample size. That's how the standard error for an average or a percent is going to go down. Okay, by how much? Well, that will depend on how this SE behaves as you increase the sample size. So let's take another look at the formula. What's the formula? It's the SD of the population, which is a constant, divided by the square root of the sample size, and this approximately is because I am ignoring the finite population correction. It's close enough to 1 that I'm not going to bother. Alright, so now I want to increase the sample size so that this whole thing gets multiplied by a third. It's got to come down by a factor of 3. So what should I do to the sample size? Should I just multiply it by 3? Will that give me a 3 in the denominator? Well, there's this annoying square root. That might actually end up giving me a square root of 3 in the denominator. You know what I'm going to do? I'm going to try a factor not of 3 but of 3 squared. That is 9. Let's take a look at what happens. So my standard error for the sample average is going to be the box SD divided by the square root of the sample size, which is now 9 times my old one. Rules to do with square roots: you can split the square root into 2 bits. The square root of 9 times n is the square root of 9 times the square root of n. What's the square root of 9? Yep, it's my 3. And so my standard error, when I multiply my sample size by 9, is 1/3 of the old standard error that I started with. And that's what I wanted to do. And so what have I learned? I have learned that if I want 3 times the accuracy, I better multiply the sample size not by 3 but by the square of 3, which is equal to 9. It's because the sample size is not the denominator, it's the root of the sample size. That's the denominator. And so what's the moral of this story? What would I need to do if I wanted 10 times the accuracy? I'd have to multiply by 10 squared, which is 100, would I not? Yeah, and so I need a really big sample. And why is that a problem? Well, because that's a resource problem. You got to go and find all of those 100 times as many people as you need. And so what you're learning is that accuracy doesn't come cheap. You want more accuracy? You got to increase your sample size and by squares. So just be prepared for that. Usually, this observation that we've made, which is that to multiply the accuracy by a factor, you have to multiply the sample size by the square of the factor, is stated backwards, like this. Supposing I've got a sample size, and I multiply it by a factor. What happens to the accuracy? Well, it goes up by what? Not by the factor, but by the square root of the factor. Numerically, what just happened here? I had a sample size, I multiplied it by 5. Did my accuracy go up by a factor of 5? It did not. It went up by a factor of root 5, which is 2 and a bit. If I wanted the accuracy to go up by a factor of 5, how big should I have made the sample? I should have multiplied the sample by 5 squared. I should have multiplied by 25. If you just multiply by 5, your accuracy goes up by root 5. And this is called the square root law, and it is very universally applicable when you are doing simple random samples and you're looking at standard errors for percents or averages. It gives you a very good sense of roughly how big your samples have to be. And just to make sure that we are confident about what are the important elements in looking at accuracy and what we can ignore, let's take a couple of natural ideas and examine them in light of the specific calculations that you've now learned. So I'm going to take a comparison of two cities. The first one has 1 million people and the second one has 4 million people. And I'm going to take a simple random sample of 0.1% of each city. Now 0.1%, as we've seen before, is 1 in 1,000. And so I'm going to take 1 in 1,000 of each city. And the question I'm asking is, are the two samples about equally accurate? Because I am sampling the same percent in each city. Other things being equal, are the two samples about equally accurate? And let's take a look at other things being equal. Okay, so what goes into accuracy? There are two things. There's the SE for the average that computed the old way, and there's the finite population correction. And these involve the SD of the population, the sample size, and the population size. Well, the population sizes we know, the sample sizes we can figure out. What we are assuming, other things being equal, is that the two population SDs are the same or at least very close. In that case, are the two samples about equally accurate? You're sampling the same percent. Well, let's see. Sample sizes? 1 out of every 1,000 of these people, 1 out of every 1,000 of those people. So sample A has 1,000 people in it and sample B has 4,000 people in it. Sample sizes definitely not the same. However, pretty small relative to the population size. So if you compute the correction factors, surely those are going to be close to 1. You can work it out. And those are not going to make a huge difference one way or another. Other things being equal, we're assuming that the two population SDs are about the same. And so what's different? The only thing that's different are the sample sizes. So what is the SE for the sample average? Well, in the case of sample A, it's this sigma divided by square root of 1,000. And in the case of sample B, it's the same sigma divided by square root of 4,000. And which of those two SEs is going to be smaller? Was the one that's coming from the bigger sample. And so no, the two samples are not about equally accurate. Sample B is more accurate. It's about 4 times as large as sample A. It might be close to 2 times as accurate. Square root law. And so that is an observation that is very important to make that accuracy depends on the absolute size of the sample, not the relative size, when you are sampling a small fraction of the population. Of course, if your sample was bigger, then you could no longer ignore the correction factor, and then you would have to take a number of things into account. But in the typical statistic situation where you have a huge population and a relatively small sample, it's the absolute size of the sample that affects your accuracy, because sigma divided by root n. And which n? The sample size. The population size only figures in the correction factor, which is a non-entity because it's awfully close to 1. And this takes some wrapping your head around, because people feel, well, I'm sampling the same percent, I should have the same accuracy. Not so. And just to make sure that we have no ifs, ands, or buts about that, let's just take it the same situation, but a different sampling scheme. So same two cities being compared, 1 million versus 4 million, and now I'm going to take a simple random sample of 1,000 people from each city. Same question. Other things being equal, that is, the standard deviations of the two populations being about the same, are these two samples about equally accurate? Because they weren't when the percent was the same. Are they about equally accurate now? Well, let's see. What do we know? We know that the two correction factors are close to 1. You can just calculate them. 1,000 out of a million, 1,000 out of 4 million, those correction factors are going to be very close to 1. As before, we're assuming that the two population SDs are about the same, other things being equal. That's what that is implying. And now the two sample sizes are also the same. So if you compute the standard error for the average, what are you going to be doing? In both cases, you're going to be taking this sigma, which is the same in both cities, and you're going to be dividing by square root of 1,000, which is the same sample size in both cities, and so your standard error is going to be pretty much the same in both cases, and so the two samples are indeed about equally accurate. It is the absolute size of the sample that matters, not the size relative to the population, provided, of course, you're sampling a small fraction of the population. And while some of you are seeing this numerically, I know that there are people who are looking at this going, you know what, there's something wrong with this. 1,000 of a million, I'm sampling a bigger fraction of this population. Compared to 1,000 out of 4 million, I'm sampling 4 times the fraction here. So how come this is equally accurate? It's a reasonable question. The mathematics says they're about equally accurate. It is very important to have a physical sense of why they are about equally accurate. And for this, I want you to imagine not a population of people, but I would like you to imagine a liquid that is a mixture of ones and zeros, basically. How about 20% alcohol, 80% water? And you and I both have that mixture of liquid. I have a bucket of it, and you have an enormous great bathtub. Same liquid, 20 alcohol, 80 water. And what we do is I take my bucket and you take your bathtub, and we slosh our liquid around and we mix up the alcohol and the water really, really well. So I'm holding a bucket of this mixed up liquid and you are holding a bathtub. Well, I hope you're not holding it. You are standing next to a bathtub of precisely the same liquid. They've all been thoroughly mixed up. Right, so what happens next? What happens next is that each of us has a test tube. I'm holding a test tube and you are holding a test tube of precisely the same size. Tiny relative to both our big containers, but compared to each other exactly the same. So I take my test tube and I put it in my bucket and I draw out a test tube full of the liquid. You take your identical test tube, you put it in your bathtub, and you take out a test tube full of liquid. Now we started with the same liquid. Both of us mixed our liquid up, and now we stare at our two test tubes. could you really tell if I just mixed up the test tubes which one was yours and which one was mine? I don't think so. You're going to have about the same information in your test tube as I have in mine. The issue is not that you were drawing from a bathtub and I was drawing from a bucket. The important thing is that we mixed up our liquids. We randomized. And if you randomize, then your sample of 1,000 people is going to be equally accurate in both cities. Your test tube is going to look the same whether you drew from the bucket of liquid or from the bathtub of liquid. And that is a perhaps slightly unintuitive result, but it is true and it is the basis of sampling. And oh, you are ready. You are ready to do your own polls. And that's going to be the business of STAT 2.3x, which is our next move.